Hello, AI enthusiasts. Welcome to a new deep dive. Building on our previous talk about decision trees, we are ready to scale up. Here is what most tutorials never tell you about random forests. They are not just a collection of trees, but a sophisticated system of checks and balances. By the end of this video, you will finally understand how a crowd of imperfect models creates a single, near-perfect prediction, a deep insight which most explanations completely skip. Think of it like a single judge versus a full panel. A lone voice can be biased, but a group finds the truth. A single decision tree is like a brilliant but narrow-minded judge. Because it tries so hard to learn every detail of its case files, it often memorizes noise instead of patterns. We call this overfitting. If we change just a few facts in the data, the tree's entire logic might flip, leading to a completely different and potentially wrong verdict. This instability is the primary reason we need a more robust approach. Instead of relying on one expert, a random forest assembles a diverse panel of judges. Each judge represents an individual decision tree. By themselves, these trees might make mistakes or overfit to specific details. However, when we combine them, their individual errors tend to cancel each other out. Diversity is the secret sauce. If every judge looks at the exact same evidence, they will all reach the same biased conclusion. To prevent this, we give each judge a slightly different set of case files to review. One judge might focus on specific witnesses, while another looks at physical evidence. Because they see different subsets of the data, they develop different perspectives on the problem. When it is time to make a prediction, every judge in the forest casts an independent vote based on their unique training. For a classification task, we simply take the majority ruling. If 60 judges vote guilty and 40 vote not guilty, the forest's final verdict is guilty. This voting process, known as aggregation, smooths out the eccentricities of any single tree. Visually, the difference is striking. A single decision tree creates a jagged boundary that often hugs the noise in the data too closely. But as we add more trees to our forest, the combined boundary becomes smoother and more generalized. It stops chasing every outlier and starts capturing the true underlying shape of the data. This is how the forest achieves better performance on new, unseen information. Real-world data is rarely just two-dimensional. In complex cases, like predicting a patient's health, judges must weigh dozens of different features simultaneously. Imagine one judge specializing in blood pressure while another looks at age and genetics. Together, they cover the entire landscape of the problem more effectively than any single expert could. Mathematically, we are reducing the variance of our model. Think of it as a crowd guessing the number of jelly beans in a jar. Individual guesses might be way off, but the average of 1,000 guesses is usually remarkably accurate. In a random forest, the noise of individual trees cancels out, while the true signal gets amplified. One of the most powerful features of this algorithm is its ability to tell us which variables matter most. We can track how often our judges rely on a specific piece of evidence to make their decisions. If most judges frequently use blood sugars to make a correct diagnosis, the model ranks that feature as highly important. This transparency helps us understand the why behind the forest predictions. You might think that more trees are always better, but there is a point of diminishing returns. Adding the first 50 judges significantly improves the panel's accuracy. However, going from 500 to 5,000 judges might only offer a tiny gain while increasing computation time. Finding the right balance between forest size and speed is a key part of the design process. From a single, unstable tree to a robust forest of diverse experts, we have seen how collective intelligence transforms machine learning. By giving different judges different perspectives, we create a system that is more than the sum of its parts. If you found this deep dive into the forest helpful, consider exploring our next video on gradient boosting, where we learn how judges can actually learn from each other's mistakes. See you in the next one. Subscribe to learn more about the power of ensemble machine learning.